Okay, so in this video we'll talk about Schrödinger's equation, which is the basic equation of motion in quantum mechanics. Okay, so let's see, you all remember the axiom of unitary evolution, which says that a quantum system evolves by unitary rotation of the Hilbert space. So by some unitary rotation u. But we can ask, which unitary rotation do you use? And this is the answer. This is a question that Schrödinger's equation answers. Okay, so Schrödinger's equation gives us the quantum equation of motion. All right. So to describe Schrödinger's equation, we must first focus on a particular observable, the energy observable, which is usually denoted by H, and it's called the Hamiltonian of the system. So the eigenvectors of H are the states of definite energy, and the eigenvalues are the energies of the corresponding states. So let's just do an example to get ourselves straight on this. So let's say that we go back to our example of a hydrogen atom and the electron. Right? We think of the electron is in one of several states. The ground state, which is lowest energy state, the first excited state, and so on up to the. If we limit its energy, then maybe there are only k different orbitals that come into play, and so we have the orbitals all the way through k minus 1. Now, how did we pick these states? Well, these are the states of definite energy. This is the ground state. It's the lowest energy state. That's the next highest energy state, and so on. And of course, by the superposition principle, in general, the state of the system is a superposition over all of these states. Okay, but now when you have a superposition like this, what is the energy of this state? Well, we don't know. It's in a superposition of states of definite energy. And so if we were to actually write down the energy observable, so if you were to write out the Hamiltonian for the system, well, what would it look like? The states of definite energy for this system happen to be the basis states, 0, 1 through k minus 1. And so, and what are the energies? Well, maybe the energy of the ground state is E0, the energy of the first excited state is E1, and so on up to ek minus 1. And so the Hamiltonian is a diagonal matrix in this case, and the eigenstates of this Hamiltonian, which are the basis states, are the states of definite energy. And of course, the general state of the system is a superposition over these eigenstates. It's a superposition over these basis states, and those are not states of definite energy. Here's another example. It's an example of an observable we've seen before. It's let's say we call it the Hamiltonian of the system. So it happens to be this one, H here, which is minus half on the diagonal and 5/2 on the off diagonal. Now this was an observable which had two eigenstates, plus and minus, and the eigenvalue of the state plus was 2 and of minus was minus 3, and so this would correspond to saying that if this was the Hamiltonian of the system, you would have two states of definite energy: the minus state, which would have the lower energy, minus 3, and the plus state with energy of plus 2. Okay, so now in terms of this Hamiltonian, the Schrödinger's equation is a differential equation that tells us how the state psi of t. So we want to know the state of the system at time t, which we denote by psi of t. We want to know how it evolves in time. So, for instance, we might be given psi at time 0 and the Hamiltonian of the system, and we want to know what's the state of the system at time t, say after 1 unit of time or 10 units of time. And so this is described by Schrödinger's equation, which is a differential equation, which says d by dt of psi t is proportional to h times psi of t. So that's a very funny thing. It's a differential equation which involves an operator, h. Okay, so how do we even come to grips with this? So we'll see how to do this in this lecture, but then we'll, over the next lecture or two, we'll get more and more of a feel, an intuitive feel for what Schrödinger's equation is. So we'll study it from 2 or 3 different viewpoints. The other thing here is there's a very important thing here, which is that it's I times d psi by dt, where I is, of course, the square root of -1. And this is quite important because this is what leads to the unitary evolution. And finally, h bar is a reduced Planck constant. It's h over 2 pi, where h is a Planck's constant, which is a physical constant reflecting the size of energy quanta. Okay, so now, how do we actually understand Schrödinger's equation? How do we solve Schrödinger's equation? So we want to, we are given psi at time 0, and we want to understand what psi at time t looks like. Well, it turns out that the key to solving Schrödinger's equation is understanding the eigenvectors of H, the states of definite energy. So they evolve in a very nice way. So let's say that our initial state psi at time 0 was one of the eigenstates phi sub j of this of the Hamiltonian, and let's say that the corresponding eigenvalue was lambda sub j. So this is the energy of the eigenstate phi sub j. So then the claim is that our state at time t is just, it's still phi sub j, the same eigenstate, but with a phase associated with it, e to the minus I lambda sub j t over h bar. Okay, so I hope everybody understands what I mean by phase. It's a unit complex number. So if we are looking in the complex plane, this is the real axis, that's the imaginary axis, that's the unit circle. This is a unit circle, this is 1, this is I, this is -1, minus I. And if you look at a number here at angle theta, then it's e to the I. Okay, all right. So that's as far as this phase is concerned. So what's this telling us? It's telling us that if you start off in an eigenstate of H, then the state evolves by just a change of phase, right? So the overall phase in front of this state changes, but that's all that happens, and the phase rotates at a rate that's proportional to the energy. So the higher the energy, the quicker the phase rotates. The lower the energy, the slower it rotates. Okay, so now how do we see this? Well, since phi sub j is an eigenstate of H times phi sub j is just lambda j times phi sub j. Okay, so what this means is that the change in the differential change in the state at time t is just proportional to phi sub j itself. And so what this implies is that at every time the state is going to still point in the direction of phi sub j. The only question is, what's the amplitude, right? So this implies that psi of t, if you start with psi of 0 equal to phi sub j, the eigenstate, then psi at time t must look like some constant a of t times phi of j. Okay, so now we can go back and solve our differential equation. So we have I h bar d by dt of a of t phi sub j is equal to h times psi of t, which is h times a of t phi of j, phi sub j. This is a constant which we can pull out, so that's a of t lambda sub j phi sub j. And phi sub j, of course, doesn't, there's no time variance, and so what we get is d a of t, just rearranging by a of t, is equal to lambda sub j over h bar, divide by I, which is minus I, dt. Okay, so I'm just rearranging this. And this is a simple differential equation. We all know how to solve. It's just it just gives a of t is e to the minus I lambda jt over h bar. Okay, which is what we wanted. So now we understand how an eigenstate of h evolves under in time. So what Schrödinger's equation, solving Schrödinger's equation, tells us is that if you start with an eigenstate of h, then the state always points in the same direction. All that changes is the phase, and the phase changes via this precession rule. It precesses at a rate proportional to lambda j, which is the energy of that eigenstate. So now, of course, in general, our starting state is not going to be an eigenstate. It's going to be a superposition of eigenstates. So we might start with the starting state superposition over phi sub j with amplitude alpha sub j. So then, of course, by linearity, the state at time t is just going to be the sum over j of, this is always, of course, sum over j of alpha j e to the minus I lambda j t over h bar phi sub j. So basically, each eigenstate, or each state of definite energy, it sort of stays invariant in time, except it precesses, right? Each eigenstate is precessing at its own rate. It marches to its own drummer. Which drummer? Well, it's its energy. And that's the basic equation of motion in quantum mechanics. Okay, so now we could also try to write this out as an operator. So if you want to know how to get from the state at time 0 to the state at time t, well, there's clearly a linear operator that tells us how to map from time 0 to time t. And if we write it out in the eigenbasis of h, it is a diagonal matrix, because each eigenstate sort of stays invariant except for phase changes, and so it's a diagonal matrix with diagonal entries e to the minus I lambda j t over h bar. Okay, so now this is clearly a unitary matrix, right? If you call this matrix U, then clearly U satisfies U times U dagger equal to U dagger. U is the identity. Okay, so another way you can write down this postulate, the axiom of unitary evolution, is you can just say, well, evolution is by Schrödinger's equation. If you solve Schrödinger's equation, you get this, you get unitary transformation for evolution in time. Okay, so sorry, I should call it U of t. Okay, same here. And the other thing we can do is, u of t is now e to the minus I ht over h bar. So this is just notation. You can think of it as e to the a is a matrix. If you write a matrix B equal to e to the a, then B has the same eigenvalues as A. So sorry, B has the same eigenvectors as A. Eigenvectors, but the eigenvalues of B are the exponential of eigenvalues of A. So if one of the eigenvalues of A is lambda sub j, then the corresponding eigenvalue of B is e to the lambda j. Okay. So this is just you can take it as notation. You can think about it as a Taylor expansion, but just think of it as notation for matrix exponentials. Okay, so finally let's do an example. Suppose our Hamiltonian is X, the bit flip matrix, and we start off in the zero state. Then what's the state at time t? Well, so we all know the eigenvectors of X are plus and minus, with eigenvalues +1 and -1. So what we need to do is first write psi of 0 in the eigenbasis. So psi of 0 is 1 over square root 2 plus 1 over square root 2 minus. And so psi of t is going to be equal to 1 over square root 2. And what does plus evolve to? It evolves to e to the minus I lambda is 1 t over h bar plus 1 over square root 2 e to the minus I lambda. Lambda in this case is -1, so we get a plus t over h bar minus.